One thing to note or to remember is with concentration, remember that this is just molarity, and we solve for molarity by taking moles divided by liters. So sometimes you might have to determine the concentration of the species before you plug it into the equilibrium constant equation. Okay, one thing to note too, with the equilibrium constant K, so specifically for the K constant, okay, we can only plug in equilibrium concentrations. Okay, or numbers. It's not always concentration. Sometimes we could also have like Kp, which is partial pressures of the different species. Okay, but we have we can only plug in the numbers for at equilibrium for the equilibrium constant K. Okay, we're going to talk about another constant that we can use in order to determine where the reaction is, in which way it's going to shift. But we'll talk about that here in a little bit. All right, so if we had an equation, let's just say we had N2, which is a gas, plus 3H2, also gas. Okay, and then this just shows that the reaction is reversible. So we have a forward and reverse reaction occurring. Yields 2NH3, which is also a gas. Okay, so if we were finding the equilibrium constant equation for this, our Kc would be equal to products over reactants. So we're going to have our product, the concentration of our NH3, okay, raised to the second power because of its coefficient from the balanced equation, and then over my reactants, so my N2 just raised to the first power because it has a coefficient of 1, and then my H2 raised to the third power. Okay, so we can have two different types of equilibriums. We can have homogeneous equilibrium or heterogeneous equilibrium. Okay, so for homogeneous equilibrium, the example like the one that we just had, we had N2 gas plus 3H2 gas yields 2NH3 gas. Okay, so in this instance, all the species are the same state. Okay, so they're all gases. So this would be a homogeneous equilibrium because we're dealing with concentrations of 3 gases. Okay, we're heterogeneous equilibrium, we're going to have other states of matter in our balanced equation. So for example, if I have CaCO3, which is a solid, yields CaO, also a solid, plus CO2, which is a gas. Okay, so here we have different states of matter, which makes it a heterogeneous equilibrium. Okay, one thing to note is that when we are determining the equation for our equilibrium constant K, pure solids and liquids are left out of the expression. Okay, so if we were writing an expression for this equation, this heterogeneous equilibrium, okay, our Kc would be equal to our products, okay, and the only product that would be relevant would be this one because it's a gas. We would not include this because it's a solid. So I would have my bracket, CO2, okay, it wouldn't be raised to anything, okay, and then over my reactants, okay, for my reactant side, I have just a solid, which I wouldn't include, so this would just be like over 1, okay, which we wouldn't need to include, okay. If I was writing this with partial pressures instead, remember I would use that Kp as my constant. Okay, and with partial pressures, the formatting is a little bit different. Instead of using brackets, we actually use parentheses, and we actually put P, which stands for pressure, and then we put what the species is below it, so CO2. Okay, and then if we did have a coefficient out in front, we would put the exponent outside of the parentheses. Okay, so like I mentioned before, we also have a reaction quotient, and which is denoted with a Q instead of a K. So this just tells us the relative conditions at any moment during the reaction. So where are we at in the reaction? How close are we to getting to equilibrium? Are we going to have to go forward in order to get equilibrium, or are we going to have to go in reverse in order to get equilibrium? Okay, generally when we are calculating the reaction quotient Q, it's usually going to give us initial conditions. Okay, so it might be like initial concentrations, so then you can determine which way it's going to go, or it might be like initial pressures, partial pressures, and then we are going to determine which way it goes. Okay, so if our Q value that we calculate is equal to our Kc value, our equilibrium constant value, okay, this means that we are at equilibrium. Okay, for the next one, we have that our reaction quotient Q is greater than Kc. Okay, so if we are greater in the Q value, that means we've gone too far in the reaction. Okay, so what we're going to need to do is we're going to proceed in the reverse direction. Okay, in order to bring it back to equilibrium. Okay, so if Q is larger than K, that means we've gone too far, so it's going to shift in the reverse direction. Okay, if our Q value is less than K, that means it hasn't gotten to equilibrium yet, so it's going to have to go forward in order to catch up or reach equilibrium. So we're going to proceed in the forward direction. Okay, so that's kind of how I think about it whenever I'm comparing the two. So if Q is larger than K, that means we went too far, so we have to go in the reverse. Whereas if Q is less than K, okay, it hasn't reached that equilibrium, so it needs to continue forward to get to equilibrium. Okay. So let's do a practice problem. Here we have a balanced equation. It says the reaction above takes place at 300 Kelvin and is allowed to reach equilibrium. The equilibrium concentrations of CO2 and CO are 2.5 molarity and 0.35 molarity respectively. Okay, so for part A, it wants us to write the equilibrium constant expression, Kc, for the reaction. Okay, before we do that, I do just want to note, because I did forget to talk about this in a previous slide, but they will tell you the temperature. And as long as they tell you that the temperature is not changing, it does not affect anything to do with our equilibrium constants or our reaction quotients, okay? It's just given information, it's just telling you that the temperature isn't changing, so it's not going to affect the rate. So we're only focusing on concentrations in this particular equation or question, okay? So when we go to write the equilibrium constant expression for Kc, we're going to do products over reactants. Okay, if we look at our equation, our balanced equation for our products, we're not going to include the carbon because it's a solid, so we'll include the CO2 gas on top, just raised to the first power, divided by our reactants. We only have one reactant. It is a gas, so we'll include it. So CO raised to the second power. So let's go ahead and write that in. We are going to use brackets because this is concentration. Okay, so that is our expression for K. All right, so then for part B, we're going to calculate the value for Kc at 300 Kelvin. They did give us the molarities for each of the species that's included in the expression, so we just have to plug those in. So Kc is equal to 2.5 divided by 0.35 squared. Okay, so we're going to get a Kc value of 20.4. Okay, we didn't use this information in our equation, so that's why we did not use that in order to determine sig figs. So we'd have 3 sig figs here because both concentrations that we used had 3 sig figs. And it is just a constant, so it doesn't have a unit. Okay, for this next one, the reaction was placed in a rigid 2-liter container and the total pressure was monitored as the reaction proceeded. So here we have data. Okay, notice that over time, okay, the total pressure in the container changed, okay, until this point, whenever it stayed the same. So here we're assuming that's when our dynamic equilibrium occurred. Okay, so our concentrations, well, in this case, the pressures were not changing anymore. Okay, so we assume that it has reached equilibrium. Okay, so first off, we're just going to write the expression for Kp. Remember, for Kp, we use slightly different symbols. We don't use the brackets, we use parentheses. So the pressure of our product, which is CO, raised to the second power, divided by our reactants. We're not going to include the carbon because, again, it's a solid. So we're going to say the pressure of CO2 is raised to the first power. I didn't have to put that in parentheses. I usually just do because it's habit. Okay, so for part B, it says at equilibrium, the partial pressure of CO2 is 1.63 atmosphere. Okay, so at equilibrium, the two things that are applying pressure to the 2-liter container is our CO2 gas, if there's any remaining, and our CO gas. Okay, so if it tells us that the partial pressure of our CO2 is 1.63, and we know that the total pressure of the canister is 8.37, I can determine the partial pressure of CO just by subtracting. So 8.37 minus my 1.63, and the partial pressure of carbon monoxide is 6.74 atmosphere. Okay, and then it asks us to actually calculate or determine the equilibrium constant. So we already have the expression, so we just have to plug in our partial pressures for each to determine what our Kp is. So our Kp is equal to the partial pressure of our carbon monoxide, which is what we solved for for the initial part of this part B problem. So 6.74 squared over our reactants, which was our CO2, and the partial pressure they told us was 1.63. Okay, so when I put that through my calculator, I'm going to get a Kp value of 27.9. And again, that's not going to have a unit. Okay, and we have one more part to this problem. For part C, in a different experiment at the same temperature, the partial pressure of CO is 5.31 atmosphere. Calculate the partial pressure of CO2. Okay, so we're not going to be using this data because this data was from the initial experiment. This is a separate experiment, but they did tell us that the experiment was done at the same temperature, which means that the Kp is going to be the same. So Kp remains the same. because this was done at the same temperature as well. So the rate is going to be the same. Okay, so if we use the equation that we used previously, we had our Kp is equal to our CO squared over our partial pressure of CO2. So if I plug in the Kp value that I found for part B, part 2, I got 27.9 is equal to, and then they told us the partial pressure of carbon monoxide, so 5.31, and we're going to square that over the partial pressure of CO2. So we can solve by that by multiplying over my partial pressure and then dividing both sides by 27.9, and I got that the partial pressure of the CO2 is 1.01